have the pleasure today to have a really fantastic, very well-known, renowned scientist that has worked with every president since President Carter in the White House as an advisor. He has the National Medal of Science that he received from President Obama. And he really is National Academy of Engineering, chair of any number of National Academies groups, and he's the chair of the U.S. Global Change Research Program advisory group. So it really, the list is almost too long to say what Warren Washington has accomplished in his life. So he's gonna take us a little bit through that journey and tell us how he and what he's done. So, but it really is. It would be worth it for you to look up who Warren Washington is. It really has done an enormous amount of things, and much of the science that we do today is in part, in great measure, of the advice that he's given so many administrations over the past 25 years or so, right?
Yeah.
Or more?
More.
It is a pleasure to have him here. So we wanted to have a little recognition for you, and so we have, the students have something for you. So, you take the box out. You want to?
Is it a new car?
I wish our grant would allow that.
Wow.
So we know that you've been also very involved in mentoring graduate students and undergrads, and you care very much about that. So in recognition of your work and your mentoring and teaching and your contribution to science.
Thank you.
Who would like to?
So one thing I'd like to make sure we do when we have someone like Dr. Washington is for our students to be here, because he's been such an exemplary role model throughout his career in terms of not only being a pioneer in his field, but also being a strong advocate for really having a true diverse scientific and engineering workforce. And here at USF and in the college, we've tried and we've wanted to have that. And also for the students who are going to go on in their careers, that's something that we all want and want to continue to strive to have, for future generations. So we're very honored for this. So I promised my student I would take a good picture. So I don't want to disappoint them. So let's see how I do here. I'll take one more here.
Don't forget the selfie, Bernard.
I think I got one. That's good.
Thank you. Could that be mailed to me? Thank you. Thank you very much.
I just want to point out one more thing for those of you interested in his career and his history. He's written a book with his wife, who's edited it. Mary is here as well. Thank you for coming, and I wanted to share this book exists if you'd like to copy it.
Well, thank you very much for inviting me down here and having me an opportunity to see what's happening here. I'm impressed. I'm impressed with the students, the faculty, and everyone who's associated with this. And I just learned from Frank that you have a regular program to invite visitors to come in from the outside, and how enriching that is for the educational process to bring in people like myself to give a chance to sprinkle some new ideas and to discuss old ideas. When I talked to Frank earlier, I think he was encouraging me to give not only a scientific talk, but to talk a little bit about my other activities and how I became a scientist. So I've tried to interweave that themes into my talk. Now, for some of you who are world experts in various areas, I may not quite get it right, and you can straighten me out during the question period. But on the other hand, there is going to be some new things that I'll talk about in this talk, and showing some of the new simulations that we're doing in our very high resolution atmospheric model and in our ocean models. So let me get started. And I think I need to tell on the story about the Earth's climate. Actually, there isn't anything really new about this, but I think, but for the people in the audience who aren't atmospheric scientists or climate scientists, I think it'd be good to review on what we know and what we think is going to happen. First of all, I want to show this graph from ice core data before 1958 and the Mauna Loa data after 1958. And just to emphasize, if you go back in time, if I think I can do this right, if you go back in time, so this is 0 here, going back 800,000 years, and we go through these cycles. These are on the Ice Age and interglacial periods, and these are roughly 50,000 years or more, caused by the changes in the orbit of the Earth around the Sun. So we understand that process fairly well. So if you look at the far right over here, you can see from 1958 until the present that the carbon dioxide concentration has gone up to 400 parts per million, and it's a quite different period from any of the previous 800,000 years. So that the concentration of carbon dioxide is impressive in how rapidly it's grown. And we are into a different period. Some people call it the Anthropocene. It's caused by man's introducing more and more carbon dioxide into the atmosphere. So this is a rather alarming increase, and we sort of know that at business as usual, if we don't do anything about increasing greenhouse gases, we can be up to somewhere around 850 parts per million by the end of this century. So, and the reason that this is so important is that when you burn a molecule of fossil fuel that generates CO2, that CO2 has an average lifetime of roughly 90 years in the atmosphere. Some molecules will be around for 500 years or longer, and some molecules will be around for shorter periods of time. So it isn't quite on the same as some of the people who are skeptics of climate change say. If we slow down and don't deal with this problem in our use of fossil fuels, that we can return the climate back to where it was. And sort of once it's in the system, it's going to be there for a long time, and therefore cause global warming for a long, long time. And we haven't figured out a technological way to take carbon dioxide out of the atmosphere. So if we don't cut emissions rapidly, we're going to have a major problem by the end of this century, and a much different climate, I might add. Now, a lot of people have speculated that the cause of recent climate change is due to variations in the solar radiation coming from on the sun. And here, if you go back to 1977, when we started measuring on the sun's intensity from satellites, we're seeing here a increase and a decrease every 11 years or so. And we have understood a lot about what causes these things in the sun's radiation that comes off. But the bottom line, if you look at over these 3 periods, there really hasn't been an increase of carbon, excuse me, of the forcing from the sun. It's relatively a small increase or decrease compared to the increase of CO2. So I think the argument for the sun causing on the recent increases is a false argument. Here I want to show on the recent data from NOAA, and what you're seeing here is the globally average surface air temperature. And you can see that from, say, the 1950s, there's been a relative increase. And we expect that for this year, 2015, it'll be even a larger increase. And part of that's caused by the El Nino, of course. But on the bottom line is that on the increase is significant and increasing as we would expect. And I didn't show what our models are showing for the same period, but we also see a very similar pattern, almost overlapping with this observed curve in terms of the globally average increase. In fact, this shows the El Nino years and the La Nina years. And as I said, we're in an El Nino year. During the El Nino years, and we tend to have warmer global temperatures, and La Nina years, we have cooler. But anyway, on the way to probably look at this is that El Ninos and La Nina years kind of introduce a noise factor into the record. There are 2 views of global warming, what the climate scientists are saying and what the skeptics are saying. Here's what the deniers say. They pick out a year and then they go down and they say that that's causing cooling. But they're forgetting that there's an overall trend, which is upward. So you shouldn't pick a high and a low year to make assumptions about trends. This just shows that you ought to look at the overall trend and not the individual years. There are a number of research articles which explain some of these cooling events on the short term. I won't have time to kind of go into that, but some of them are caused by volcanic dust that gets into the atmosphere from the volcanic eruptions. This is what the El Nino pattern looks like in the Pacific. And you can see that there's very strong warming along the coast and along the equator. And this is a typical El Nino pattern. And what's probably a little bit unusual about this is the El Nino pattern is one of the strongest that we've seen back in recorded history. So probably in the top 10 bracket. Now, if you look at the globally average for just sort of 1 year, sort of 1 month, this is what you kind of get. And you get sometimes a cooling pattern, and you get warming patterns, and you'll see some computer animations I'll show later where these kind of monthly patterns are very natural and they cannot be precisely explained, but when you take annual averages or 10-year averages, you can see where the warming patterns really are. This is me at a younger age when I had hair. I just want to impress the younger people in the audience that I was once a student, and this is how I looked at that point in my life. I think in this picture, this was probably about 1975 or so, when I was lecturing to young students about climate modeling. So I wasn't that so much different than you young folks. In the 1950s and early 1960s, there were only 4 groups in the world who were actually doing climate modeling. And there was a group at a place called GFDL right here, Suki Manabe and Joe Smagwinski. And there's another group at UCLA, Yale Mintz and Arakawa. And then Chuck Leith at Livermore National Laboratory, and Dr. Kasuhara and myself at the National Center for Atmospheric Research. I actually started getting into this way back in 1959 when I had kind of like you, I took a summer job at Stanford, and they were working on trying to put together the elements of a model of the atmosphere. And I told my advisor there, how do I get into this field? And he actually told me to write to some specific people, and I accepted a position at Penn State University. And my advisor was actually, as a teenager, the chauffeur for Albert Einstein and his famous father, who was the premier art historian from University of Hamburg, and he escaped Nazi Germany and went to Princeton Institute for Advanced Study. That's where he ran into him. But anyway, that's another interesting story, which I can tell you about some other time. On the laws of physics and chemistry and biology can be expressed in terms of mathematical principles, and I think I won't go into detail, but anyway, in the early days, we had much simpler models of just the atmosphere, and then the oceans came later, sea ice and vegetation came later. And we learned how to solve these on early computers, and I mentioned this afternoon. The computers that we ran on had less computer power than the iPhone that you have in your pocket, but they were as big as this room. And just to show you how the technology has advanced, now we run on computers that have 100,000 processors, and they're as big as this building. And we started to include in our models precipitation, radiation, and vegetation, and boundary effects of heat and momentum and moisture at the Earth's surface. And then we did experiments with changing greenhouse gases, the volcanic eruptions, and solar variations. So it was a long ride, but we succeeded in many ways. And here's on the principal actors. This guy is Bjerknes, V. Bjerknes. He's the one who first wrote down the principles of solving these equations in 1904. And then here's L.F. Richardson right here, who was a conscientious objector in World War I. And the war in World War I in Europe were episodic. Nothing happened for a long period of time. Then you come out of the trenches and have a bloody day or so. And then and he worked for the Red Cross transporting people in the south of France. But in between battles, he actually tried to solve these mathematical equations in great detail. And he wrote a book about it, which is really outlined what we had to do to solve these mathematical equations and how we can solve them and so forth. So he failed in his forecast because he didn't have good enough data to put into the model. But he actually set the agenda for us later folks to use electronic computers to solve the equations. And these two gentlemen, Jules Charney and Norm Phillips, carried out a more simplified model than Richardson did, but carried out the first weather forecast with a much simplified set of equations. So they essentially solved on these five actually it's 1, 2, 3, 4, 5, 6 equations and 6 unknowns, and this started weather forecasting as well as climate modeling. And this sort of schematic, and I won't go through this in great detail, essentially shows what we include in our models nowadays. For example, we have several different types of clouds. We have radiation, both solar and infrared radiation. We have lakes. We have river flow. We have introduction of carbon dioxide and other greenhouse gases from the Earth's surface. We have sea ice. We have vegetation. We have, in some versions of the model, we have biological interactions and ecological interactions. So all of these now are integral